Hey everyone, welcome back to Linear Algebra. This will be lecture 22 of the course, and in this section we're going to discuss the dimension theorem. And so let's go ahead and jump into it. So we're going to call this section 5.3 the dimension theorem. And so what we're planning to do here is we're going to introduce two special subspaces. So given a linear transformation from a vector space V into a vector space W, we're going to introduce two special subspaces. So first thing is what's called the kernel. Okay, so the kernel, and this is going to be a subspace of V. And then the second one we're going to talk about is the range of the linear transformation. The range, we'll say, of L. And this is going to be a subspace, naturally, of W. Okay, so that'll be, first up will be, let's talk about those two. And then those two subspaces are what is, are the kind of the key ingredients of the famous dimension theorem. Okay, so first we'll do this. Secondly, we'll talk about how these two subspaces are related to the rank of a matrix. Okay, so we'll get to that. And then after we've done all that, a kind of profound but relatively easy to prove given the machinery that we're going to introduce here, we're going to talk about how the rank of a matrix has a rank of a matrix and the rank of its transpose are the same. A matrix and its transpose have the same rank. So we'll get into that as well, right? So that's kind of the plan. And so all of these things, what these things all have in common is the dimension theorem. Okay, so let's go ahead and get started by discussing what we mean by the kernel. Okay, so definition, we're going to let L be a linear transformation from V to W. Okay, so we've got a linear transformation. The kernel, okay, sorry, let me write that so you can actually read it. The kernel, the kernel, and we usually say the kernel of the transformation itself, the kernel of L. Okay, and it's denoted by just the ker and then the name of the transformation. So the kernel of L is the subset of vectors in V that map to the zero vector in W. Okay, so that's the kernel. The kernel is all the vectors in V that map to 0 under the linear transformation L. Okay, so another way to write it would be to say that the kernel of L is equal to the set of V and V such that L of V equals the 0 vector in W. Okay, so that's kind of a set notation way to think of it. Okay, and so that's what we mean by the kernel. And so then while we're defining things, let's talk about the range. These are similar items. Well, they're totally different kinds of subsets, but or subspaces, but they're both subspaces. So let's knock this one out as well. So the range of L then, and this one, of course, again, L is a linear transformation from V to W. We say that the range of L, and usually the way we describe it is just the word range, like that's a notation for that. So the range is the set of vectors in W that are the image of some vector from V. Okay. So that's what we mean by the range, and then we can of course put this in sort of set notation here. We say the range of L, and that's going to be equal to the set of images under L such that V is in V. Okay, so basically, I mean, this has the same feel as, you know, the range when we're talking about a regular like function, right? We say the range of a function is all of the values that are the image of the under the function. Okay, so it's the same idea here. And so important to keep in mind, and maybe you can see this clearly by the way this is written out, but the kernel is a subset of V, and the range is a subset of W. All right, so we just want to make sure we keep straight the fact that the kernel is all the elements in V that map to 0, so it's a subset of V, and the range is all of the vectors in W that are the image of some vector from V. So it naturally is a subset of W. Okay. All right. Okay, so we've got that. Those are the kind of prerequisite definitions. Now we've got a nice theorem that we can build off of. Oops. Theorem. Okay. And so if L is a linear transformation from V to W, okay, it's a linear transformation, then the kernel of L is a subspace of V. Okay, so it's a subspace, and the range of L is a subspace of what? W. Okay, so we already knew there were subsets, and so this just naturally, the next thing we'd want to be sure of is, okay, are they subspaces? And indeed they are. Okay, and so the proof of this is pretty immediate. It's pretty immediate, right? So the kernel of L is the pre-image of a subspace, right? So we won't go through the formal proof here, but we can kind of think this through. So the kernel, right? This is the pre-image of this, right? Of the 0 vector in W, right? The 0 vector in W taken alone is a subspace, right? It's a subspace of W. Okay, and so if the kernel is the preimage of a subspace, then we have a theorem previously that we talked through that says that the kernel has to be a subspace as well, right? So this implies that the kernel is a subspace, right? And so this is more or less the proof. You could write it up a little nicer, but right. And then for the same reason, the range is the image of a vector space. It's also a vector space. So similarly, we'll say the range of L is the preimage of, is the image, not the preimage. I meant to write image. Is the image of, a vector space. Right, and so for that reason, the range is a subspace as well. Okay, and so that's basically what the proof looks like. I'll just put proof here, right? Even though it's a little conversational, but you get the idea, right? It follows directly from this other theorem. Okay, excellent. All right. So let's do an example. Let's get an example out. Make sure we understand what's happening here. Examples are key. You get a definition in a theorem, you better ask for an example next. Okay, so let's say for n greater than or equal to 3, we want to consider the linear transformation from Rn to Rn. Okay, and then we'll say it's given by, we'll let L work on an n vector, a1, a2, an, naturally. And we'll say that that's equal to A1, A2, 0, 0, dot, 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 0. Right? So basically, L maps any n vector into a vector that has all zeros except for the first two components. Okay, and so what is the kernel here? So the kernel of L is the vectors in Rn. All right, all the vectors in Rn that map to the zero vector. Okay, so this is obviously an n vector here. Okay. Right, and so what does that look like? Well, I mean, there's not just one, right? In this case, there's lots of ways to write the kernel. So the kernel here is basically going to be what? It's going to be all of the vectors of the form 0, 0, A3, A4, AN, right? Such that A3, A4, dot, 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 AN are real numbers. Does that make sense? Is that clear? Yeah, I mean, basically, right, because, you know, if you look at what the linear transformation does, the only two components that are relevant are the A1 and the A2, so those just have to map to 0. The other n-2 vectors can be pretty much anything you want because they all automatically get sent to 0, right? And so there's an infinite variety of vectors in Rn that could be mapped to the 0 vector, okay, in Rn, right? And so that's the kind of thing you can see. So depending on the linear transformation, there may be only one item in the kernel, or there may be infinite items in the kernel and everything in between, naturally. Okay, and so what does the range here look like? Right, so what's the range look like? Well, the range is going to be all of the items in Rn that are mapped by L. Right, so the range is all of the items in Rn that are mapped to by L. Right, that's kind of the definition. Right, so what's a way to write that? Well, we could say the range of L, it's equal to all the vectors of this form, right? A1, A2, 0, dot, 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 0. Right? And so the only thing to worry about is A1 and A2. So A1 and A2 are real numbers, but everything else in the vector is 0. Okay, perfect. So that's our first example. Okay, a couple things to note here. So note, the kernel of L, right, is a subset of Rn, right? That's obvious, right? And it's a subspace. Okay, what else can we say? Well, the range is a subspace as well. Right, this is just the previous theorem. Okay. What are the dimensions? Right, so if we think about what are the dimensions? If we think about the kernel and the range that we just looked at, what are the dimensions? Remember the kernel, right? Remember we said that the kernel is the set of all vectors that were 0, 0, A3, dot, 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 AN, such that AI is in R. That's the kernel. And then we said the range was equal to the set of vectors A1, A2, 0, dot, 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 0. Okay, so the same thing. So what are the dimensions? What's the dimension of the kernel? So what's the dimension of the kernel of L? Well, the kernel, right, that's this one, right? So these two mean nothing. They're always 0. So it's really n-2, isn't it? Okay, Okay, so the dimension of the kernel is n minus 2. Right, and we can easily see this, right? A basis for this would be just the standard basis vectors. A basis would be, you know, E3, E4, dot, 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 En. Right, and that's obviously going to be n minus 2. It's going to have size n minus 2. What about the range? What's the dimension of the range? So the dimension of the range of L, well, that's this guy. Again, these all the zeros don't matter. It's really just A1 and A2. Right, so the dimension there is clearly 2, and a basis would be E1 and E2. Right, so that's how you can tell what the dimension is, just by thinking about what a basis would have to look like. Okay. Okay, and so that's the first example. So we've looked at a linear transformation. Turns out it's a linear operator, actually. Right, because it's on the same subspace, Rn to Rn. Sorry, the same vector space, Rn to Rn. And we've identified the kernel, we identified the range, and we've identified the dimension of both as well. Okay, let's take another example. Okay, so we're building towards the dimension theorem. We want to see some upfront examples first, and then we'll kind of you should be able to see by the end of the set of examples I have picked out that what we're looking at. So let's consider a linear transformation from P3 to P2. Okay, and it's going to be given by, these are polynomial vector spaces, given by, okay, so if I apply the linear transformation to a third degree or less polynomial, so ax cubed plus bx squared plus cx plus d. What I'm going to do with this linear transformation is it's going to map to 3ax squared plus 2bx plus c. Okay, and so what is this? Well, this is basically differentiation, right? It's just differentiation of a polynomial. And so what's the kernel? What's the kernel here? Well, we got to think about what kind of vectors in P3 would map to 0. So basically we have to think about 3ax squared plus 2bx plus c equaling 0. When is that going to happen in the case of a polynomial? Well, it's going to happen when, I mean, looking at this, a, b, and c are 0, right? This is 3, this is 2. The only time you're going to get a 0 on this term is if a is 0, and the same for the others as well, right? So if and only if a equals b equals c equals 0. And so when is that going to be true? Well, if I take polynomials from P3, so I've got ax cubed plus bx squared plus cx plus d, right? So when is this going to be 0 after the linear transformation? Well, a's got to be equal to 0, so this term will be 0. B's got to be equal to 0, so that term is 0. And c has to be equal to 0, so that term is 0. So the kernel is going to be equal to basically the constants, right? It's just a set of constant polynomials. So the kernel of L is going to be equal to, and I'm going to write it all out. This is certainly not how you'd want to write it, but just to make it plain, 0x cubed plus 0x squared plus 0x plus d, such that d is a real number. Okay, and that's the kernel. Okay. Now what's the dimension of this? Well, this is just a one-dimensional vector space, right? The dimension of the kernel in this case is just 1. Right? What's the basis? Well, the basis, a basis is just 1, right? If you think about the standard basis, all we need is the constant term from the standard basis, so that's just that, and of course that's got one vector in it, so the dimension is 1. What about the range of this linear transformation? What's the range of this? What's the range? What is the range of L? Well, so the range is going to be the set of all the polynomials, right? So it's going to be the set 3ax squared plus 2bx plus c. So the range is going to be basically all of these polynomials. Okay, and so this is actually going to be all of P2, right? You can think any P2 polynomial can be represented here, right? If I want something that's less than the second degree, then I could just make A0, right? Right. So this is just all of P2. So the range of L is all of P2. Okay. Okay, so that's the range of L. And what's the dimension of the range here? Well, it's P2, so it's going to be 3, right? What's the basis? Think of a basis. The standard basis here would have to be x squared, x, and 1. Okay, and so that's the standard basis for P2, and so that means the dimension of P2 is 3, and so therefore the range is 3, has a dimension of 3 as well, since it's equal to P2. Okay. All right. Okay, very good. Okay, and so between the previous example and this example, we may be noticing something, right? So in the first example, we said that this was the Rn example. For example 1, we said that the dimension of the kernel, all right, what did we say the dimension of the kernel was? I'll have to flip it over here. I think we said it was n minus 2, correct? Yes. And the dimension of the range, we said, was 2. That was in example 1. And then the example we just saw, we said that the dimension of the kernel was 1, and the dimension of the range was 3. Okay, and so the dimension theorem says something about the relationship between these two, the dimension of the kernel, the dimension of the range, and specifically the sum of the dimensions here. And so in this case, dim cur plus dim range is equal to n minus 2 plus 2, which is n. And in this case, the dimension of the kernel plus the dimension of the range is equal to 1 plus 3, which is 4. Okay, and so the dimension theorem is what we're going to look at next. But keep in mind that this was the dimension of the vector space, V. This was also the dimension of the vector space, V. Right? And so the dimension theorem ties the dimension of the vector space, V, to this relationship between the kernel and the range. Okay, so here's the theorem. And this is, again, called the dimension theorem. Okay, very, very nice theorem from linear algebra. A lot of very elegant theorem. Okay, and so here it is. So if L is a linear transformation from V to W, okay, we got a linear transformation, and V is finite dimensional, then the range of L is finite dimensional also, and the dimension of the kernel plus the dimension of the range is equal to the dimension of V. Okay, so whatever this guy is, then the sum of the dimensions of kernel and range is equal to the dimension of the vector space V. Okay. Okay, very good. So that's the dimension theorem, and we're going to prove it. I do think it's going to be one of the more challenging proofs that we have done in this course, but we're going to prove. We're going to push through it because it's such an important theorem, and the proof has a lot of really great moves, right? So it's a lot of great techniques and things to think about with linear algebra, and I think it's a key theorem, and so let's go ahead and prove it. Okay, so let's write a proof here. Proof of the dimension theorem. Okay, so we're going to naturally assume that L is a linear transformation from a vector space V to W. It's a linear transformation. And then the other thing we have to assume is the dimensionality of V is finite. Okay, so the dimension of V is finite. Okay. So we know that the kernel of L is a subspace of V. Right? Kernel of L is a subspace of V. We know that from the previous theorem. And so we know that the dimension of the kernel of L is less than infinity. It's a finite number. Right, and we know that because of a previous theorem, and also common sense would say that, right? But let's go ahead and let the dimension of the kernel be set equal to S. So we'll let the dimension of the kernel equal S. Okay. And so if the dimension of the kernel is S, then any basis for the kernel is going to include S vectors. And so let's let K1 through Ks be the set of basis vectors. Okay, all right. Okay, so that's our basis for the kernel. And let's define Q1 through Qt let's let these be vectors in V. These are going to be vectors in V such that a basis K1 dot 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 Ks comma Q1 comma dot 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 Qt. So this set, when I take the S vectors that form the basis for the kernel and the T vectors that form the basis, this is going to be a basis for V. Okay, right, and so what we're saying here is that, right. So what does this mean? Hence, we say therefore the dimension of V is S plus T, right? So it's S plus T. Okay, so another better way to write that would be to say the dimension of V is equal to S plus T. Okay. All right. So we've got this basis, the set of basis vectors K1 through Ks, union Q1 through Qt. And so what we're saying is the dimension of V is S plus T, and we know that the dimension of the kernel is T. So what we need to really see is that what does this S come from? Okay, so here's where things can get a little tricky. So we're going to claim that C, which is equal to This is going to be the linear transformation on Q1 and ... linear transformation on Qt. We're going to call this thing C, and we're going to claim that it consists of t vectors and is a basis for the range of L. Okay, so we claim that this set C consists of t vectors and is a basis for the range of L. Okay, how are we going to do this? Well, this is going to be interesting. Let's see. So obviously, but if we can show this, then we're done, right? So if we can show this, we are done. Right now, why are we done? Does this make sure? Does this make sense? Are we sure we'll be done? So we'll be done because the dimension of the range, if we can show that this is a basis for the range, then what we'll have shown is that the dimension of the range of L is equal to t, and we've already assumed that the dimension of the kernel of L is equal to the S, and we also have that the dimension of V is S plus T, right? So that's the theorem, right? So how are we going to show this one? These two we've kind of set the thing up, to show these two. These two are more or less assumed, and what we'll see is that if we assume these two, then this one gets forced out. Okay, and so let's do that. Okay, so let's flip this page here. So let's talk about the range a little bit, what we know about the range and how it relates to some of these things. So the range of L, it's a subspace of W. Okay, it's a subspace of W, right? And so what it means, what the range of L means, is that if I've got some V in V, some vector in V, given some vector in V, I can write V as A1 K1 plus A2 K2 plus ... plus AS KS, right? So these are all of the SK vectors, right, that all, form the basis for the kernel. Plus, and then plus we've got these other ones, B1 Q1 plus B2 Q2 plus ... plus BT QT, right? Okay, and so all we've done here, right? We've assumed that K1 through KS and Q1 through QT is a basis for is a basis for V, right? And what we're trying to show is that this other piece is the range. If this is the kernel, this other piece is the range. Okay, right? So this is all perfectly fine. And remember, A1 through AS and B1 through BT, these are just real numbers, right? This is a linear combination. Okay, so nothing fancy there. Okay, now all we're going to do is we're going to apply the linear transformation to this linear combination, right? So if I plug V into the linear transformation, then what I'm doing is I'm plugging in this linear combination. So that's just going to be L of A1 K1 plus ... plus AS KS plus B1 Q1 plus ... plus BT QT. Okay, so these are all vectors. Okay, and we know that if we apply a linear transformation to a linear combination, we can break the thing up, right? We know that we can rewrite this as A1 times L of K1 plus ... AS times L of KS plus B1 times L of Q1 plus ... plus BT times L of QT. Right? And so that's no problem. Okay. So again, this is just properties of a linear transformation, right? Now, what happens to L of K1? right? Remember, K1 through Ks, these are a basis for the kernel, right? So what happens up front here, this becomes A1 times the 0 vector plus ... plus AS times the 0 vector. Right? These are all just 0. Well, the 0 vector, right? So then I'm left with these guys. Well, I should leave the L on, sorry. Okay, all right, so I've got this. And of course I can, once these are, if these are all the 0 vector, then 0 times A1 is all just still the 0 vector, and when I add them all up, I'm still just the 0 vector. And so I can just drop them, right? And so what I'm left with is B1 L of Q1 plus ... plus BT L of QT. Okay. Right, and so what does that mean? Well, what we're saying here is for an arbitrary V in V, an arbitrary vector V in V, it can be written like this, as a linear combination of Q1 through Qt. And so what does that mean? Well, it means that the range is spanned by this set here. The range of the linear transformation is spanned by, well, this was C, we'll call it C again, L of Q1 ... L of Qt. Okay, and so that's getting us very close to the idea that this could be a basis for the range. Right? We don't know that it's a basis yet. Why don't we? All we know is that it spans the range. Right? Anything that's in the range can be written as a linear combination of this, means that it spans the range. What we don't know is that these vectors LQ1 through LQT, we don't know that they are linearly independent. We need to show that next. Okay? So if it spans and is linearly independent, then we've got a basis. Let's see if it's linearly independent. Spoiler, it is linearly independent. Okay, linearly independent. Okay, so let's, how do we show that? Well, remember what we can do. We can say C1 times L of Q1 plus ... plus CT times L of QT. We can start with this. We suppose this is true. Okay, so suppose this is kind of like, you know, this is the criteria, right? What we need to show is that all the CIs are equal to 0. Okay, so let's suppose this is true. Then that implies that L. So basically, we can do the reverse of what we did up here. We can, instead of having the separate linear transformation on the vectors, we can apply the linear transformation to the entire linear combination. So L of C1 Q1 plus ... plus CT QT. Right, this must be equal to 0 as well. And what does that imply? Well, what that implies is that this linear combination is in the kernel. That implies that C1 Q1 plus ... plus CT QT, whatever that happens to be, is in the kernel of L. Right? If this linear combination, when we transform it under L, equals 0, then by definition that means this linear combination is in the kernel. Okay, and so what does that mean? Well, that implies that there exists D1 through DS, right, real numbers, such that what? Well, such that this guy here can be written in terms of the basis for the kernel. Okay, so we're going to flip pages here. And let me rewrite this last section just to make sure we have it all on the same page. So C1 Q1 plus dot 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 plus CT QT we see must be in the kernel. Okay, and so that means there exists D1, D2, dot dot dot, DS, real numbers, such that, right, such that what? Well, such that this thing here, it's in the kernel, so C1 Q1 plus dot 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 plus CT QT. That's going to be, we can re-express whatever this vector is in terms of the basis for the kernel. So D1 K1 plus dot 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 DS KS. Okay, so this is these K, right? K1 dot 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 KS is the basis for the kernel. Okay, just remember where that came from. Okay, and then what does this mean? Well, taking this thing, well, basically we can subtract off all of the C1s, right, and bring them to the other side. So we could have this D1 K1 plus dot 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 plus DS KS minus C1 Q1 minus dot 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 minus this guy CT QT. That would all equal the 0 vector, wouldn't it? Okay, but what's going on here? What are we doing here? So this is, again, this whole linear combination must be in the kernel as well, right? Okay, but so something very tricky here, so make sure you catch this. I'm going to write it very, very explicitly. So this here, okay, combined with the fact that there's a basis for the kernel, K1 dot 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 KS, and, okay, hold on, Q1 dot 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 QT. All right, this is a basis for V. Right, and that's going to imply, what does that imply? That implies that it's linearly independent. And what does that mean? What does that imply? Well, that implies that D1 is equal to D2, which is equal to dot dot dot, equal to DS, which is equal to C1, dot dot dot, equal to CT, equal to 0. Okay, and so these are all 0, and that means that the CI's are 0, and therefore C must be linearly independent. So, right, let's kind of sum this up. So the CI's are all equal to 0. That implies that C that we had before, right, C being the set L Q1, comma, dot, 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 LQT is linearly independent. Okay, so that C is linearly independent, right? And we saw that C was that C spanned the range, and now we see that C is linearly independent. Okay. Okay. So we're basically, we have shown that it's a basis. One thing that could be problematic is that there could be duplicates in here, right? So let's think about how that could be, right? We just kind of came up with this, this collection, but how do we know that there's not duplicates in here, right? So let's just to be clear here. So C spans the range. C is linearly independent. But how do we know that C is, all the vectors in C are distinct? Well, it kind of comes along with the fact that it's linearly independent, right? If C did not consist of t distinct vectors, right? So think about this. If C did not consist of t distinct vectors, then this couldn't have been true, right? C1 L Q1 plus dot 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 plus CT L QT equals 0. We wouldn't have the implication that all of the CIs are 0 like we did. Right? So if C did not consist of t distinct vectors, then it would have been possible we could have had this without every CI equal to 0. But we did see that that was true. We saw that every CI must have been 0 because of the argument previously. All right, so we're done. Right? So that means we're done. Right? And so we've shown that if the kernel is defined to have dimension S, and if the vector space V is assumed to have S plus T dimension, and along with the way we've kind of set it up, then what that forces out is that the dimension of the range is T. Okay, so again, this is a pretty tricky proof, but again, I think people can. I think it's definitely within the grasp of the course. Otherwise, I wouldn't have brought it up. So let's talk about what's happening here, like structurally, kind of top down. Okay, and so basically, you've got a vector space V, and you've got a vector space W. Okay. Now inside of V, you've got a subspace that we call the kernel. Okay. Now inside the kernel, you've got K1, K2, dot, 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 Ks. We'll call those basis vectors. Okay. Now all of those basis vectors are going to map to a single vector in W, which is the 0 vector. Right? So all of these go to the same place. Okay. So all of those vectors that map to the 0 vector we call the kernel. Now similarly, inside of V, you've got other vectors, Q1, Q2, dot, 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 and in this case, we'll stick with the notation from the previous proof. So you've got Q1, Q2, Qt, and together, K1 through Ks and Q1 through Qt form a basis for V, right? And but these guys all map to non-zero vectors. Right, so over here you've got like L of Q1, L of Q2, dot, 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 L of Qt. Right, and so these guys all map over like that. Okay, so this is kind of like what the picture looks like. Okay. All right, so you've got vectors that map to 0, you've got vectors that map to non-zero. Okay. And so the range is naturally going to be spanned by these guys here. Right? So everything that's non-zero over here is going to be the range. Okay, and obviously this is going to be the basis. This is going to be a basis for the range. Right? And this is a basis for the kernel. You might have lots of things that go to 0. Okay. All right, very good. Okay, so I think we're gonna split the this lecture into 2 parts. So we'll kind of stop here, and then we'll pick this up in a part B lecture. Okay, so join us again for the part B section.